if you trace back every single one of these species, you find that stump is the same. You find a common stump. And that common stump is where life emerged about 4 billion years, 3.94 billion years ago, and has since then branched out into different species. And we are just one of the branches on the tree. We are no different than any other life form, except that we're just a different species. But every species on the planet, we share common ancestry with. We are cousins to every animal, every plant in some way. If you go far back enough, we humans are ancestors, are the cousins to every living being, even plants. Humans and plants are very related. Fungi, bacteria, we are all related. We're cousins. It just depends on how far back you go to see where our common stump is, see where the common splitting is, right? Where is the common divergence? And that's what this tree of life can do. Now, when it comes to human evolution, there were many other apes before us, right? You can see primates right here. Like when I was talking about the tree, once you understand the tree of life, you understand this better. Primates are a category of mammals. Now, these early primates, about 50, 30, 40 million years ago, they split off to lemurs, monkeys, these gibbons, right? And over time, right, those primates became monkeys. They split off. Some of those became apes. Split off again. Some of those became great apes, like orangutans and gorillas. Split off again. Some of them became humans. So if you go far back enough, you find that we share common ancestry with bonobos, gorillas, and orangutans. What this means is that very not too far long ago, us and gorillas and bonobos shared a common ancestor, right? And that's what that means. If you go far back enough on the tree, we find that us and the gorillas and orangutans of today share a common stump, a common splitting on the tree, about 6 million years ago. And since then, we have changed, and there are many humans on this line between us then and today. Many other human species existed alongside others. And here's a great example of the different types. This is not a human. This is a type of ape, but the last ape that was before humans, called Paranthropus. Australopithecus afarensis was also on the edge between human and non-human. It's on the edge. This is the last common ancestor that between us and the apes. The first human species definitively was Homo habilis about 2 million years ago. 2 million years ago was one of the first human species. So these guys are human. Okay. You see how over time they look more and more like us, right? Homo erectus about 1.5 million years ago. These guys discovered fire. These guys were not dumb. They were very smart. They likely had language too. Heidelbergensis, another species about 800,000 years ago. Very much human. Not us, but human. Not Homo sapiens, but Heidelbergensis. Homo georgicus, another recent Homo species. And here we are, the Neanderthals. This is a Neanderthal which existed up to 50,000 years ago. Very recent. They, in fact, existed alongside humans, us, Homo sapiens. And these Neanderthals, some of us, we have DNA of. Some of them mated with the sapiens right here, right? This is us. This is our species right here. But this species, well, you can call it a subspecies, was very close in terms of genetics with us, which such that they could reproduce with us. And some of them did. And that's why some of us today have Neanderthal DNA in us. And that's our history. You know, and where do all humans come from? Well, most great apes come from Africa, right here, Central and Eastern Africa. And over time, they walked. Climate change, a lot of climatic changes during the time forced us to move, leave the trees, go onto land and grasslands. Some of us went to Western Africa, some went into the Middle East, traversing through Asia, Eastern Asia, Southeast Asia, even Australia, about 15,000 years ago, 50,000 years ago. Some humans split off and went to Northern Asia or Middle Asia. And then you can see there's a time where they also met each other, right? Some went to Northern Asia, Siberia, modern day Siberia and Russia, the Arctic. Humans traverse the entire globe, and that's really what makes us human. The ability to adapt, right? Europe. Humans were in Europe about 40,000 years ago, okay? Before any of your religions, before Islam, before Christianity, before Hinduism, there were humans in Europe. Cavemen did not know religion. And about 20,000 years ago, the humans in Northeast Asia, it was cold enough during the Ice Age for a land bridge. See, this is Alaska, and this is Siberia, right? You can see there's a bridge that allowed us to traverse through this land into America. The reason why is because there was ice here. Okay. And a lot of those went to South America 15,000 years ago. The Andes, the Aztecs lived there. You can see now we live everywhere. Okay, we have taken over the entire planet. It's because humans know how to take advantage of the environments. We know how to adapt very well. We know how to survive very well. And that's why we're here today. You know, it's just incredible that we are able to do that. You know, no other species could do that. Yeah, we walked, and that's why we're the best walkers. There is no other species on the planet that walks like we can. Humans are the most efficient walkers. Even if you're pregnant, you can walk. Did you guys notice that? Even women who are pregnant, 9 months pregnant, 8 months pregnant, they can still walk. It is because that's how we evolved. We are walkers. We are foragers. We foraged. Yes, we hunted sometimes. But we walked. We were curious. What drove us into these new lands was our curiosity, and that's where we get it from. What is there? Are there resources? What is out there, right? That's what constantly drives us to move forward. What is out there? You know? We want to know. So we go. And now we're here today, able to, you know, with that same curiosity, with that same drive, but instead of exploring the world, we now explore space, right? What's the next frontier? Space. What's out there? What's up there now, right? What's up there? So this is where we get our humanity from. This is where we get our humanity from. Our ancestors, who were also afraid of the dark. They were scared. That's why we are scared as people today. Right? Oh, who's that? Is there a monster hiding in there? We're also tribal animals. We live together in tribes. That's why we get scared when some other religion gets on our way. Oh, they're Muslim or they're Christian? Oh no. They don't believe what I believe. Let's kill them. Let's harm them. See, we get that from our ancestors. The good and the bad. So now we are here. And we have become a global species. There is no more isolated tribes. They don't exist anymore. And there may be a couple left. But now we are a global species. And we are learning our ways, trying to understand each other. So, in a way, it's poetic that we are the most advanced species to have ever existed, the most capable species, yet the most violent, the most hateful, the most bigoted. It seems like our reptilian brains haven't caught up to our technology. But we're getting there. There is progress, and that's what we fight for. So yeah. Any other questions about this show? Yeah, exactly. It makes sense now, right? The context is important. I think understanding our history is so incredibly important. People ask all the time, where do we come from? Or if you want to know what we are, learn about the past. If you want to know where we're going, learn about the past. It's the key. How does natural selection work? Well, all it means is if you have a population of, let's say there's a population of giraffes, and there is in the environment there is a tree that is 20 feet tall. Now, most giraffes are 18 feet tall, but one particular giraffe is 20. And can reach the top of the tree, and hence it can get more food and survive better. And that tall giraffe also is able to reproduce because it gets more food. So because of that tall giraffe spreads its genes, it reproduces, and it makes another tall giraffe, and that giraffe has more tall giraffes, right? So the number of giraffes, if the environment allows it or dictates it, the number of giraffes that are tall will increase in that given environment. Okay, and that's how that happens. Phenotypical changes over long periods of time eventually lead to genetic changes. And if there's enough time, very different genetic changes can occur. And that's what a new species is. New species emerges after so many generations. And if the environment changes, then the species changes, right? And for the past 4 billion years, that's how it has occurred. Nature selects which species survives or dies. And the ones who survive, they do. The ones who die and cannot keep up, they go extinct. Survival of the fittest. Very brutal. Very brutal reality, right? It's a very brutal thing. But that's how nature is. Was the result of a cascade of chemical processes. It is composed of several important compounds. So deep in the oceans, we have heat sources and amino acids. These amino acids can turn into peptides. They clump together. These amino acids, they can form and combine together into peptides, longer chains. And these longer chains can form longer chains of polypeptides. And these polypeptides can form sheets of amyloids. So these are sheets of amino acids that, if they get long enough, they break. And those broken parts, those broken halves, can form new peptides, new amino acids, and new sheets. So these sheets can build upon each other. And that's is what we think was the first metabolism. Now, a cell, if you look at a cell, it's just really a clump of fat, right, that surrounds the inner parts. These are fatty acids, lipid molecules. Now, lipid molecules have two sides to them. One is hydrophilic, one's hydrophobic. One doesn't like water, one does. So when you have a chain of these molecules in the oceans, they want to form a spherical shell because they're polarized. So they form this little bubbly shell that encapsulates those amyloids, that encapsulates those amino acids. And there you go, you have the first protocell. Okay? Again, these are processes were happening simultaneously in the oceans about 4 billion years ago. So it's a very particular sequence of processes that had to occur to enable this to exist. But that's what we know so far, right? There's much more to it, but this is the very basics. It also turns out that those amino acids are very similar in structure to nucleobases. Sugars, phosphates, when combined with these nucleobases, can generate RNA. RNA contains some of the first genetic code. So again, RNA is formed by these amino acids that interact in certain ways, then interacting with certain phosphates that exist in clay minerals, which means that they typically are going to, these amino acids, these nucleobases are going to be seeping up to the surface, interacting with rain, the environment, and that's going to catalyze even more reactions. Okay, so we have that process happening until we get nucleic acids, right? RNA. RNA is nucleic acid, a very complex one. Why is it complex? Because it underwent chemical evolution, right? It underwent a vast series of complex reactions. But once you have RNA, bam, you have life. Once you have a specific RNA molecule that can replicate itself without any outside requirements, anything new, just that RNA, well, there you go. You have a living being. And here's a great example of these nucleotides that may have polymerized RNA. In other words, this is the formation of RNA. Clay particles can attach to it, catalyze reactions to become RNA molecules. So there you go. Here's the process in which RNA becomes DNA. RNA self-replicates via ribozymes. Then RNA forms from, RNA catalyzes protein synthesis. Proteins, in other words, those ribozymes can generate proteins. And then you have RNA coding for DNA and protein, right? DNA is just activated RNA. Certain proteins are produced, generating DNA. Now, this process itself also had to undergo chemical evolution, but the point is, this is how it basically happens. So, very complicated stuff, guys. Like, this is why people don't understand abiogenesis, because it's super duper complicated. Even I don't really understand it, right? But this is the basics. And again, the dividing line between life and non-life is very blurry. There is no one molecule that makes you alive. It's not a molecule. It's not an object. Life is a process. Okay, it's a specific process. Metabolism, reproduction, replication. That is life. So it's not what molecules are. It's what they do. It's what these molecules do that makes you alive. You're alive right now, not because of what you're made of. It's because of what you're doing. Right now, you're metabolizing things in your body. Your cells are metabolizing. You probably ate just recently. That food is being converted into energy that fuels your cells, right? You're drinking water. That water goes into your cells. Your cells use it to metabolize. You have sex. You reproduce, right? You replicate. That's life. It's a process. And we, as humans, are a system, a very complicated system of many, many, countless reactions happening. And these reactions emerge. Emergent of these reactions are you. You. Me. Right? I am the result of all these reactions happening in my body. And that's life. We have created protocells. We have created lipid bilayers. We have created RNA in labs. We have done these things in labs under natural conditions. There is enough evidence. Now, we haven't created life from scratch in terms of, one day there's no life, the next day there's life. We haven't done that. But you don't need to do that. We have enough evidence to show that, yeah, you can get life from these basic ingredients. We don't need to know the exact, process. As long as you know the general idea, we have a good enough evidence set to say, yeah, this is likely how it happened. No other explanation even remotely comes to explaining what abiogenesis can. So, yeah, people think it's so mysterious. It's not mysterious at all. So, what other questions do you guys have? The most important lives always get the least amount of views. Is evolution a random process? No. Evolution is not an inherently random process. It's deterministic. Why do you think that humans are the only species that evolved to this level of rationality? Good question. Why are we so different from the other animals? Well, number one, we manipulate things with our hands. We have opposable thumbs. These thumbs have allowed us to manipulate our surroundings with tools, right? Those only heighten our sense of abilities. But humans are a particular species that left the trees in Africa. We stopped. See, our ancestors lived in trees their entire lives. They lived in trees. They would climb up in trees. They would swing on the branches, and they would live there in trees their entire lives. But our ancestors were driven out of that setting into grasslands, into the savannas of Africa. They were forced. And because of this, we had to adapt to the new environments. We had to walk further. Walking helped us become human. Because we explored new places, we had to develop new ways of adapting. Right? We had to become smarter to adapt. So that's one reason. We also developed the ability to use our thumbs and hands and manipulate our surroundings. The other key invention was the fire. Fire accelerated our abilities. Now we were able to cook food in certain ways and preserve food in certain ways that we could not have before. We also developed language, right? There is a particular brain structure called the prefrontal cortex that is responsible for language, hand signals, language, symbols, right? These enabled us to communicate more effectively than any other species could. So I can pass down knowledge to my kin, and they can be taught more effectively. So all these together, right, allowed us to become who we are. Now, when you realize that about 12,000 years ago, we developed the first civilizations and farming. Okay, we used our knowledge to do this. That only accelerated it even more. Okay, now we have an even greater acceleration of changes. Because now we can all take collectively, as a trusted civilization, trusted society, share our knowledge, use our abilities for the benefit of all. Okay, and that's what catapulted our abilities. Okay, so look, there is nothing inherently special about humans. It's just that we took advantage of the edge we had. And that's it. We had a slight edge in intelligence, and we used it for our benefit. But I understand why it's so easy to look around today and say, wow, we have cars, we have buildings, this is so different than any other animal. Yes, but you're forgetting our history. You are forgetting the 2 million years of rapid exponential changes that led to us today. And there were times when our species could have easily went extinct. War, disease, famine, all those things, we were at the brink of dying at some points. But things just worked out in the way they did. And we are luckily here. So, I am, as I learn about these things, as I learn about my history, I appreciate our present more every time. Do you think we will evolve to not require as much sleep? I don't know about that. Probably. I think if we have biotechnology that can understand the brain and how it works, we'll eventually be able to not sleep at all. The CMB picture basically gathered observation and data of the universe compacted into a photo. The CMB photo, well, first of all, there's many of them. This, look, it's supposed to be three-dimensional. Right? This is supposed to be 3D. This radiation exists all around us. Even right now, there's some going through you today. Right now, there's a lot of microwave radiation going through your body from the Big Bang. Okay? The Big Bang happened everywhere you're standing, even where you're standing. The Big Bang occurred. So this light is all around us, all around the universe, because the universe was so small and dense back then. Right? So the universe, as it quickly expanded, all that light expanded with the universe, and because this light is a microwave form, we understand that in the past it was a longer form. I'm sorry, a shorter form. Right? Microwave is a long form of radiation, but X-rays and UV rays are much shorter wavelengths. So we know in the past this radiation was most likely UV or X-ray. But today it's a microwave form, and all it means is this radiation existed throughout the entire universe. Okay, it's not just a photo of a particular part. It's everywhere. This is literally a picture of the entire universe. The entire universe. A baby picture of the entire universe. In a three-dimensional sense, right? We don't know the boundaries, but we know that three-dimensionally, all around us, this is what the picture of what we can see, the observable universe is. So, yeah. Did I answer your question? Have you thought about becoming a teacher? Hell no, not today. Not anymore. Maybe 10 years ago, but not anymore. AI is going to do better teaching than anything I could do. If energy cannot be created, where did the energy of the Big Bang come from? It was always there. Energy is held in potential form. In quantum fields, energy is held in the potential form. But due to the random nature of quantum mechanics, certain fluctuations can yield that energy and convert it into kinetic. And that's what the Big Bang was. And again, if we, there's something called false vacuum decay, in which it may be the case that the universe goes back to potential again. The universe could decay back to its lowest state, called a vacuum state. So the point is, that's literally what we are. We are just a random fluctuation, it seems. And there could be many others out there. Does the universe have a cause? What do you mean by the universe? Wow, these are some boring questions. Come on, guys. We need some better questions. Explain faster than light travel. It's not possible. light travel isn't possible unless you're a photon or a neutrino or a massless particle. Anything with mass would require infinite amounts of energy to move it or accelerate it that fast. See, there isn't an exponential curve. The faster you travel, the more energy it takes to travel faster. So when you travel through the universe, you recognize that if you're going 90% the speed of light, it requires more energy to go 91% than it does to go 89%. Than it takes to go 90.5%, right? There's exponential curve in terms of how much energy it takes to get there. So if you go 99.9% the speed of light, it requires more energy than the universe contains to move you faster. How do we beat the odds of existence? That's the biggest question. We don't know the odds of existence. The odds of us existing could be 100%. 1 out of 1. What if this is the only possible world? Who says that there are other possible worlds? Maybe this is the only one. In that sense, we're the only ones that could be. There is no other chance. This is the only one. Another way of seeing it is maybe there's an infinite number of possible worlds. In that case, we're, again, inevitable. It's going to be the case that at least one universe like ours is going to happen. And there could be an infinite number of other universes just like us out there. So when we invoke odds, we typically think in our minds that there is something innately implausible about us being here. Because from our point of view, we think it's rare. But that might not be the case. We don't know what else is out there. So we can't even assess the odds of us existing or not. Explain Einstein-Rosenberg bridge. Well, that's simply referring to a wormhole. See, Einstein predicted with relativity that space and time warps, it bends. And that's what a black hole is. A black hole is a steep warping of space and time, right? A black hole is a very, very warped part of space and time. It's called the Planck energy, right? A black hole has Planck energy. In other words, the Planck energy is the limit as to how warped space and time can be. That's the limit to what we know, how much warpage could it be. A black hole has that. So we don't know what happens inside of a black hole, but we know that black holes exist. However, the Einstein-Rosenberg bridge goes a step further and says, wait a minute, if there's enough warpage, what if there's another side to that warpage? On the other side of that warpage is perhaps another region of space and time, right, that it leads to. And this could be called a wormhole. So it's essentially, that's what it is, right? It's just if you have a piece of paper like this, right here. If you have a piece of paper like this, damn, I don't know how to do it. You guys see this? Okay, so if you see this here, this is space and time, right? A flat surface, but it's curved, right? So imagine a flat surface like that, curled up. So If you saw this as a flat space, you would see that this and this side, these two sides, are very far away. But if you curl space and time up, you poke a hole through, right? You produce this wormhole. You can cut through, and now these different regions of space and time become almost on top of each other. So that's what a wormhole is. It connects two different regions of space and time together. So it could be the case that if there's enough curvature in the universe, it could be the case that if a wormhole exists right in front of me, I can go through the wormhole and not end up into another region of space and time entirely, another side of the universe. I can literally walk into it. And that's remarkable. Can black holes get smaller? Black holes can be microscopic. Absolutely. Black holes that are microscopic, however, are related to quantum fluctuations. But yes, they could be very small. It's not the size that all black holes are different, but typically the more massive it is, the more gravity it has. But black holes are very, very much diverse. Some black holes aren't that dangerous in terms of its gravity well. Some are very much not steep. Some are steep. Some black holes you can survive going near. Some you can't. You know, depends on the type. They form differently. They are consisting of different stuff. They exist in different regions. How does the universe travel faster than light? The universe doesn't travel. If you're talking about space and time, yes, space and time itself can stretch, seemingly from our point of view, faster than light. The reason why is because the speed of light limit only applies to things within space and time, but not to space and time itself. So there are some regions of the universe in which space and time is stretching faster than light, as we would calculate it. Now, again, it's not possible to objectively verify the speed of, the universe in terms of its expansion. There's no way to objectively measure that. It's all relative. But yeah, it could be the case that far away, the universe is moving faster than light. So this is called the event horizon of the universe. In other words, there might be a portion of the universe that will forever be gone from our view. It'll be black forever, because the light from those stars can't travel fast enough through that expanding space to reach our eyes ever. So that's pretty scary. Moving into what? It's not moving into anything. The universe isn't moving into new space. People want to confine the universe to a boundary, right? In our minds, we want to do it, right? Well, what's outside of the universe? There is nothing outside of it. The universe is everything there is. So if it's expanding, it's only expanding into itself. It's not expanding into some other space. However, there are some scientists who think that there could be the other dimensions in which the universe is expanding into, called hyperspace, which are 11 dimensions. So there could be 11 dimensions that are, well, at least 6 or 7 beyond ours, in which things could move within. And perhaps that applies to space. But we don't know. We don't know. I don't like looking at space. I don't like look. What happens in a black hole versus out in a white hole? A black hole a black hole pulls things into its singularity. A white hole pushes things outwards. So a white hole is really a black hole in reverse. And some people think that if you go into a black hole, you get sucked into a white hole and pushed out the other side. Nope, not anti-gravity. No, not anti-gravity. It's just you being pushed outwards at near the speed of light into other space. Because in a black hole, space and time moves, twists, rotates. It's like you got to think of space and time like ripples of an ocean, right? Like like waves of an ocean. Space and time itself can ripple. It's wavy. So, yeah, it's very, very strange. What is dark energy? Well, we think dark energy is a property of space and time. It is nothing. It's not an object. It's not like a random energy thing or a random force. It's a property of space and time itself that wants to stretch it apart. And the reason why we think is because of gravity, but reverse. It's the reverse of gravity. So gravity wants to attract things, right, with an acceleration. So if I threw a ball in the air, what happens? The ball wants to come down with an accelerating speed. But if I throw the ball up, when it comes to dark energy wants to be repulsive, not attractive. So if I were to throw the ball up with dark energy, it would go up and keep going up with an accelerating speed. So it would go up and up and up, accelerating. It would want to run away from me, right? It would want to escape from me as fast as it can. So that's dark energy, and we think that exists within all of space and time. It's pulling apart space and time itself. In other words, regions of space and time themselves are wanting to be repelled from each other, running away from each other. And that only exists, however, in the vacuum of space. It's called the vacuum energy. And if there's stuff in this empty space, this dark energy is too weak. Dark energy is exceedingly weak versus regular gravity. So anything with mass in a given volume is going to pretty much overwhelm dark energy and be too strong for it. But that's why in empty space, the space between stuff is moving, but we are not moving, right? We are not expanding because gravity is overwhelming the expansion force of the universe. So there's also many other forces that are keeping us together. But yeah, dark energy is just funnily enough, Einstein predicted it, but called it Einstein's equations predicted dark energy, but he didn't need it. He didn't think he needed it because he thought the universe was static, not expanding at all. So he thought it was just a blunder, right? He just thought, oh, yeah, it's just a random number you don't need. Because if you take it out of the equation, the universe still is perfectly static. But it turns out that we found out later he discovered dark energy. The constant. So that but he was wrong about the universe. He thought Einstein did not think the universe was expanding. We actually recently found that out. We also recently found out, like in the 90s, that the universe is accelerating in this expansion. The universe is not only getting bigger, but it's getting bigger increasingly faster. And so that's something we have seen or too. And we're always learning more about the world. When we look at it, we always learn more about it. Yet so irrelevant. Learning about space teaches us about our planet. Learning about what's out there teaches us more about who we are out here. Not just about technology and science, but it teaches us that we are rare. We are rarities in the universe. Space has a lot to teach us. Did space exist before the expansion? That's one of the biggest questions in physics. We don't know what space was before. It could be that space-time are fundamental. It also could be that they're emergent, and that seems to be the growing consensus amongst physicists, that space and time are emergent of quantum mechanics, possibly entanglement. Quantum entanglement seems to be a big factor for the nature of space and time. There seems to be a connection. So yeah, it's very strange. But there's a lot more out there. There's a lot more out there than we can see or know yet. Does the human body decompose in space? Well, yes, you will decompose slower, but you will still decompose as the microbes and bacteria will eat away at your body. Bacteria can still live in space. Certain kinds. Wouldn't we freeze? You wouldn't freeze. See, space doesn't technically have a temperature. Well, it has a temperature, but you don't feel it because there's no medium to feel it within. You know, the reason why we feel temperature is because air. But in space, there's no air. So you're not really feeling anything. There's no weight, there's no transfer of heat in empty space. But yes, it is cold. There's very little activity. Doesn't your bone density weaken? Yes, a lot of things happen to your body in space that are not good for you. Can I see the past, present, future, and event horizon? No, but you can see. Look, if you were to go into a black hole, what happens is time dilation occurs very heavily. And what this means is time for you almost stops. relative to the outside environment. People beyond the event horizon, their space and time will be way slower than yours. I'm sorry, faster than yours from your point of view. So in other words, if you were to go into a black hole, time for you would slow down. But if you were to look up at Earth, you would see Earth spin quickly. You would see the universe move fast and fast and fast. You would see the entire universe play out. Billions of years, you would see, as you go deeper and deeper into the singularity, towards the singularity. Because time for you would stop. And some people think that if you go into a black hole and you go through it and you were to survive, you're not going to survive this, but if you could, you might actually end up through a white hole, end up in another universe. Wouldn't we be surprised if in 100 years from now we're completely wrong currently about space? Well, nobody would be. I don't think scientists will be surprised if we're wrong. It's not a shocking thing. But, in fact, we expect to be wrong in science. That's the beauty of science. We get things wrong sometimes, and we learn. That's the beauty of science. But science, although gets things wrong, it's always improving, and we have a great deal of knowledge that no other realm of human endeavor can provide. Religion is not even remotely close to being as capable as what science can do. Have you addressed the Dyson sphere situation? There are no Dyson spheres. That's nonsense. First of all, Dyson spheres, there would be Dyson swarms. A Dyson sphere is way too big of an object to even consider. No intelligent being would ever make a Dyson sphere. That's ridiculous. A Dyson swarm might be more practical, but even then you need an incredible amount of material to produce it. It seems like a very inefficient way of getting energy. I mean, all you're doing is sucking up energy from the sun. We can already do that. We can already do that today. Look, an intelligent alien is never going to make those things. They're going to not leech off the sun. They're going to make their own sun by manipulating vacuum energy, by things like nuclear fusion. But also, there's lots of energy stuck in empty space. They can use to make their own stars and stuff from that. Again, hypothetical, but if these intelligent aliens exist, they will most likely do that rather than produce some kind of dumb Dyson swarm that requires more energy to extract than it requires more energy to make than it extracts. It's a very inefficient thing. I mean, you will need the mass of a planet to make that thing. And who the heck's going to have time to make an object using up energy in the process to make that thing? That's such a waste of time. Do you think astrology has any value? No. Why not? It's bogus. The planets don't dictate your life. The stars don't dictate your life. And by the way, the constellations change from our point of view every few thousand years. The idea that Scorpio or all this stuff, that couldn't even be true, even if it was. the case that these planets change your life, it wouldn't be the case that the current astrology is correct. Sailors use the stars to navigate. Yeah, absolutely. Yeah. People back then were not dumb. They were very clever. And they studied the skies very closely. And they realized that stars, if you knew the coordinates of different stars relative to your position, you can find out where you are on the Earth. If you can predict how the stars change, how they move, you can know where and when you are on the planet. So, yeah, I know people today couldn't do that. But back then, they were very keen on getting the sky correct. Yes, the Aztecs were very, very smart. They knew about eclipses, yes. Now, a lot of those guys were very, very, very crazy people. I mean, they had blood sacrifices during the eclipses. But set aside that nonsense. They were very, very clever people. They would have soccer games. They would have games where they killed you at the end if you lost. They would literally sacrifice you if you lost. And they willingly did this. Like, it was fun for them to sacrifice. Mind-boggling. Okay. I never said they were smart. I said they're clever. There's a difference. Smart means you have you're not short-sighted. They would sacrifice if they won the games. Yeah, whatever. My point remains. They would sacrifice for very bad reasons. Are you at all spiritual? What do you mean by spiritual? Is the microphone better? Have black holes had any influence on our planet? I don't think so. Can you explain special relativity? Well, special relativity shows us that light is a constant speed. Light is a constant. Speed of light's a constant. And because of this fact, traversing through the warpage of space and time while light being constant means that any movement through space can have an effect on time. It's creepy, but it shows us that time dilation occurs. Time is relative. Some people's points of view of time in one side of the universe could be completely different than somebody else's understanding of the now moment on another side of the universe. It's a very strange phenomenon, but it's a real phenomenon. We make predictions with special relativity. We need special relativity to be true in order to produce satellites, for example. GPS. If time is a spatial dimension, does that mean that everything has already happened? Time is not spatial. However, you could view it as a spatial dimension mathematically. But yes, time, if viewed as a spatial dimension, could allow you to see all events at one moment, one time, simultaneously. How has time changed in a black hole? Well, again, there's lots of dilation happening there, time dilation. Lots of warpage of space. And because everything in the universe is moving through space and time at the same constant rate, the speed of light. If you're in a black hole, you're experiencing more space. And because of this, even though your speed is through time is constant, something has to give. Your speed through the universe is constant. Something has to give. The more you move through space, the less you're moving through time. The more you move through time, the less you're moving in space, right? There's this very unique exchange. So in a black hole, you're experiencing more space, hence your experience of time is going to be less. But somewhere on Earth, we are still moving through time very quickly. We are moving through time at near the speed of light right now. But because of this, we are not moving much through space. The limits of this is where the speed of light limit is, right? Light has all of the motion in the spatial dimension. None in the time. There's no more room for motion in the time dimension. That's why there's a limit to the speed of light. There's no more space for it to traverse. It's run out. It's run out of dimension. But yeah, that's why. Space, lifeless, nothing but rocks out there. Well, yeah, there could be just planets out there and no life. It's possible. Or there could be tons of life out there. Either way, it's crazy to think. If we're alone, damn, that's scary. We're the only ones. But if there's lots of aliens, holy moly, there's all kinds of possible weird aliens out there. Do they know about us? Do any of them know about us? Hope you see this, Mike. I've been struggling with suicidal thoughts lately. Your lives help me keep me sane. It's crazy, I know. Yeah, man. Life is so wondrous. The more you learn about it, the more wondrous it becomes. The more mystery. You know, when you don't know much about the world, things seem terrible. But when you widen your scope of understanding, when you see the bigger context, you just can't help it. You just feel a sense of optimism. You feel a sense of like, damn, I'm alive. You feel a sense of gratitude. You just don't feel that way when you are looking down, right? When you look up, it's like you see a new world that gives you hope. And that's what I feel every day. Every day I learn something new, and that keeps me going. Every day I, learn something. I appreciate things more, and I'm so appreciative today, and I'm so grateful for life. my gratitude has only increased since leaving religion. And it's undescribable. Undescribable how content it makes you become. Knowledge is everything. It's the key to everything. Every problem you have, knowledge can solve. If you ever find yourself stuck in a problem, learning knowledge always helps, every time. It's just that people don't want to do it. People are scared to learn, they're scared to know. Just, See you guys later. Stay curious.